Hello everyone. So today I will talk about the end-to-end dynamic pipelining tuning strategy for small files transfer, authored by Shimin, Dawei, Shang, and Guangyan, Zhang. Firstly, I'll introduce the background and the related work. As a high-performance machine transmission protocol, Grid FTP provides 3 parameters for transmission optimization. So in different file transmission scenarios, the optimal parameter values are not the same. If the parameters are not set properly, the improvement on the throughput will be compromised and sometimes may even have negative effects. So there are many research aiming at finding optimal value for the grid FTP's parallelism parameter to improve the throughput of large file transmission over WAN. The pipelining of grid FTP is a powerful tool as well to improve the efficiency of small file transmission, but it has the same problem: how to find the best pipelining parameter. So to solve that finding optimal pipelining parameter problem, and then we try to design a data structure. It's called a bucket, right? It's only because when transmitting lots of small files, the file composition of different file sites might be different, and how to deal with those file sets with different characteristics and determine the best pipelining parameter value for them is difficult. So this is the reason why a bucket data structure is designed. And besides of that, we also propose an algorithm to determine an optimal pipelining parameters value based on this structure. So there are mainly 2 steps to adjust the optimal pipelining parameter. So the first is we do the pipelining calculation. So original intention of a bucket design is just to reduce the time complexity of sorting files. Accurate sorting based on the file size is required for getting an optimal pipelining parameter. So if the file sorting is not desirable, the files combined from the buckets for transmission might not match the target, but with a delay product well, or in short is BDP, resulting in low bandwidth utilization. So to reduce the influence of imprecise sorting, and we increase the denominator of the pipelining parameter calculation. So the second step is to do the file classification. The design of the new data structure mainly adopts the idea of bucketing used to sort files by size. To improve the bandwidth utilization, we can deliberately select the files from those buckets and then make the combined file size as close as possible to the BDP. So the drawback is using a large number of buckets for sorting all files will increase the time complexity. So our solution is we first allocate the files into different sized buckets and then select the files from the proper bucket and then create a file combination with the right size. So this figure illustrated what we did. So originally we could have 2 large buckets, but we can further divide the bucket 1, for example, into smaller sized buckets, right? So to ensure the pipelining transmission size as close to the BDP as possible, and each transmission trunk may mix several ordinary files. The mixing of several non-prioritized ordinary files will not consume too much time, and then the transmission speed of high priority file is still improved without a notable total throughput drop. So in this case, as you can see, we have a high priority files, and then they, based on their size, they are sorted into different smaller buckets, and then based on the adjustment, and then we can put it at the in front of the queue. So those are the involved algorithms. The first is file bucket divide, and the second is a transmission queue. So for detail, and you can just look at the paper. So based on the proposed data structure and the algorithms, we implement them, and then we conduct the experiments in this environment. So in the experiment, and then we build up 3 servers, and all of them are running the CentOS 7 operating system and XFS file system, and then 1 server, and then what we used as the grid FTP server, another 2 as the clients, and then also the bandwidth bottleneck is 100 Mbps, and the RTT, the round trip time, is 50 ms from the client to the server, and then double from the client to the server. And then bucket size is set to BDP in all the experiments. So so this is one of the performance analysis we've done. And then in this figure, as you can see, and we use different RTT, and then we observe the throughput by different algorithms, like the default one, or the bucket divide algorithm, and all the RCD. So as you can see, compared to the other 2 and our method, and then BD, and then could only reduce the total throughput at around 8%, while the default one, the grid FTP default transfer algorithm, and also the RCD, the recursive trunk division transport algorithm, reduced about about 17% and 14% respectively. So it's greater than our method. So, and then also the ability of RCD to process extremely smaller files is weakened when we increase the BDP. So the throughput of RCD drops significantly when the RTT increased to 100 ms. So in here, so that we have the 50 ms, but when we increase the RTT to 100 ms, as you can see, these RCD drop more throughput. And we also examined the impact on throughput by different file sizes. So as you can see, we have 2 different file sets, and this files plus has more smaller files, and also you can see the throughput of these files plus all perform better than those under condition files set, and our algorithm improves the throughput more than the other 2, right? Default and then the RCD. So the impact on the throughput when transferring high priority files with the, as you can see, when we increase the percentage of higher priority files to be transmitted in a given file set, and when we increase the number of the high priority files, and then the overall throughput varies within 3% range. And then also the file movement will also increase the size variance in our bucket structure, and making it harder to match the BDP for the immediate following combinations, which in turn causes a slightly drop. The transmission time of high priority files has also been examined. So under an even file size distribution, our algorithm is able to improve the throughput and then transmit the high priority files promptly. So, and we could not compare the transmission of higher priority files with RCD. It's only because RCD does not consider the high priority files in a file set. If we use different CC values, and then also we can observe the throughput generated by different algorithms. So again, so our algorithm, the throughput is better than those of the default and RCD. Okay? And then when we transfer smaller files, doesn't matter whether or not the pipelining parameter is used or in combination with the concurrent parameter. With the increase of transfer delay time and the number of large files, the performance of our algorithm is further improved without a notable increase of resource assumption. So you can see here with different CC value 246, and then so that's the throughput generated by those three different transfer algorithms, and our is no significant difference, even with different values of the CC. So in total, in this paper, and then a smart bucket data structure is designed for the grid FTP protocol. It is mainly used to perform classification operation based on the size. On top of this data structure, and we have the bucket divide algorithm to conduct the corresponding bucket division and then queue arrangement operations on files. With this structure and also the BD algorithm, we can not only find optimal pipelining parameter values, but also optimize the transmission throughput for lots of small files with low resource consumption. Furthermore, more than 90% of the total throughput can be easily achieved when our BD algorithm is used with the concurrent parameter. So in terms of the future work, and we could further explore to refine the model and to make the arrangement of various spatial files more accurate. And the second is we try to update the parameters for continuous influx of files in real time. Right. Thank you very much. That's all for this presentation.